So from here on out, I think it's mostly slides. So these are the case sets. I don't think we've talked about these yet, but case sets are where you define your simulation parameters. What orbit am I going to use? What heat rate, am I going to have? My radiation couplings. How many couplings do I want to have? What view factor sum do I wish to have? Am I using hot dissipations, cold dissipations? Do I have any overrides? All the different things that can vary between your case sets. This is essentially where you're defining what your simulation is supposed to do. One of the first checks that I do when I've first built a model is what I call a connectivity check. So is everything conductively coupled together? If you know there are areas that aren't coupled, like say a solar array might be kind of hanging out there, that'll be handled. It'll be coupled to space when I do it. But let's say I wanted everything except the solar array to make sure that that's coupled together. Well, I could take and make one node somewhere be a boundary node, and then I'll run Cinda. And if Cinda can solve, then everything's connected, because Cinda will fail if you have any nodes not connected to a boundary. So if I take one place as a boundary, if heat can find its way there from anywhere else in the model, my connectivity check is passed. So I know that I at least have established the conductive network. Might be wrong, but I've at least established that it's there. So in this case, when we ran it, we would have found that I think there was one thing that didn't go. So in this case, when we ran it, there are two deliberate errors that were introduced. The first was that we didn't define hot case as a register. And then the second one, and this we did in the symbol manager. And the second one was that we had Q component KK and Q component LL. Those were typos that were deliberately introduced. So at this point, the model would run, and it would fail in the preprocessor. And so that's the first place where Cinda is going to go. And when you fail in the preprocessor, basically means you've got some kind of a syntax error that Cinda doesn't know how to recognize. So we would catch these and define the hot case as a register so that it's there, and we would fix the Q component LL and KK. So now we would run it again, and now we would fail during the compile part. So it got through the preprocessor, Cinda recognized everything, but then there was some Fortran line that Fortran didn't recognize. And in this case, it was a F-type statement to call not found, and it doesn't know what not found is because we never defined not found as a function or a subroutine. So this would be the next place where it fails. So we would then remove that erroneous call not found, and it preprocesses and it compiles, and then fails during the processor point. So we've preprocessed, we've compiled, we've now executed. So now here, if you get this failure and it fails there, you would search for abnormal, and chances are, when you find that, there's some nodes that are not connected to a boundary. So in that case, it was component H that wasn't connected, and so we would add a heater mod line to component H. So this one was not connected to the rest of the system. When we make it a heater node for the whole submodel, then this would go through, and then we would essentially show that we've got connectivity. So this was the whole connectivity check with 3 sets of errors introduced at different places so that you recognize where Cinda may have problems or not like something that you've done. So when we get this out, we get gibberish. Lowest temperature is 20 C, which we had assigned somewhere. All the heat loads were working, but it doesn't make sense. This is before we've added any radiation into it. So that's a good check to make sure that you've got connectivity in your model. Then you would move on and define the rest of your case sets. So we would then add radiation tasks. We went through that. So here, again, I like to start off with 35,000 rays. I prefer a slightly lower cutoff of 0.01 rather than 0.1, which is what they have. I like the error of 1% so that it won't fire all the rays that it has. Again, never accept the default values for the names for the files or the submodels. Give them something that's intelligible so that you can recognize it. On the symbols tab, we add hot case equal to 1. We add power scale equal to 1.3. We lock the array for the beta 90. We set the output frequency to every 300 seconds. It's going to output both T's and Q's to both the output file and the save file. This is ASCII. This is binary. On the calculation tab, We select steady state and transient. We run for 4 times the orbital period. And then after running the model, we're going to display only the comp submodels and look at what their steady state results are. So this is, we've run the model, we're looking to see the results sort of reasonable or not. And so what we care about are the areas where we have dissipations. That's what we would be checking out first to see if it meets. So steady state versus transient. A lot of people like to run steady state. I've found that the younger engineers tend to believe heater numbers out of steady state far more than older engineers do. I'm always skeptical of steady state numbers. I find steady state a good starting point to get to a point where I'm not having to wait so long to reach quasi-steady. So if I run a transient from an initial condition of everything at 20, well, I might have to do this before it finally stabilizes out. If I run steady state first, it gets here, and then, okay, then it's 1 or 2 orbits. So it's just a way for me to get quasi-steady numbers quicker, but I'm going to believe what a heater's doing in transient before I would ever believe what it's doing in steady state. So my advice is don't rely on steady state numbers other than for a sanity check. Am I in the right ballpark? Use your transient cases. Find your maxes and your mins as you go through eclipses, as you go around in orbit, as things change. Because steady state just, we don't operate in steady state very often. If you're in an L2 mission, hiding behind a sun shield like Roman, fine, it's steady state. But a low Earth orbit, beta angle changes, eclipses, things cycling on and off, you just really want to use transient for that. So, and also the other pitch I'll make is if you have any stability requirements, you're not going to be able to demonstrate them with a steady state analysis. If you say you've got to be stable to 0.1 K over 200 seconds, well, you can't do that in steady state. Everything's constant. So you're going to have to get the transient. So as I see it, get the transient as quickly as you can. All right, a little bit more about the case sets. So here, we've made one of them, and now we're going to copy that one, and then we're going to change the things that need to be changed. So the hot beta 90 case, we renamed it to hot beta 75. We don't maintain unique file, or we do want unique radiation file names in this case. So we're going to change the hot beta 90 to hot beta 75. We're going to get rid of the locking. We're going to go on the symbols tab and do that. That should be local array. Select symbols, global. Edit the dissipations now. So you can, so that's, okay, sorry. So this part right here, this is one of the really overlooked and very powerful features in the case set manager. If I select a case set and I right click and I say set symbols, aliases and overrides to global values, this is now the way that I check that this case set is what I intend it to be. So now when I go and look at everything, it's based on the symbols that are defined in this case set, all the overrides, all the aliases, and everything else. So in my hot case, am I getting the right dissipations everywhere? Now if I go and look at a heat load whose dissipation has changed because the symbol has changed, now I see what that symbol actually is. So this is a great way to check, is my case set up properly as I start looking at all of the different things. One of the things you do want to be careful of, though, is make sure that if you see this message, you don't continue with the save. You want to say no, because otherwise what will happen is you might save it, and then it's going to overwrite all of your previous values with these new values that you assign. So it keeps track of the fact that this is what it was, this is what I'm changing it to because you overwrote it. When you're ready to undo that, you run the one right here that says reset the symbols back, and it sets it back to everything that's the default. So this is a good way to check that your case set is set up properly, but don't cast them as stone as the new values that everything else should be using. One of the other pieces of advice I'll offer is even if a symbol isn't going to change very often, it's sometimes wise to still put that value in as an override that's set to the same value that you want. The reason I say this is because I was bit, ran some analyses on Roman, and forgot that I had to set it to the stowed mode. So I'm running flight analyses, they're taking a bunch of time, but all my arrays are stowed, and all the high gain system is all stowed. It's like, oh, I have to go back and rerun it. So if I just said all my operational cases, I want to be the deployed configuration and put that override in there, even though the deployed configuration should have always been what it was set, it keeps you from accidentally running a configuration that you don't intend. And it can sometimes be very easy to get lost in Thermal Desktop with all the places where symbols are. So I would strongly suggest if you have a configuration that you know it's always going to be, sometimes even if you say this override is the value that it is, it can be useful. So, all right. Also here, copying case sets is easier than having to always define them from the start. If you do select multiple case sets, you can make changes to 10 of them all at once, if that's what you want to do. So sometimes it's useful. Let me take all my cold cases and select them, and then change the power factors or the scale factors, all my hot cases. You don't want to necessarily do that for defining the orbital stuff, because if that varies, you don't. But if you have things that are in common, you can select multiple cases and do it there. So this was the conclusion here. We basically get to 7 hot cases, 7 cold cases, 7 survival cases. In this case, I took all the hot cases, exported them, and then imported them back in, and then renamed and changed the things as I needed to. That made it easier than having to spawn each one separately again, when the only thing that changed between here and here were, a couple of things. So sometimes it can be easier to export case sets and re-import them back in and then modify them when you have a bunch to do, rather than trying to copy them one at a time to do that. In this case, there's also some specialized logic that I set up to output the pieces of information that I was most interested in manually to a text file. So this uses Cinda, and this would basically go through and, do I talk about? No. Output things to a file that I could easily import right into Excel in order to be able to look at the temperature. So kind of a pre-post-processing, if you will. I knew what I was going to be interested in, and so let me write the logic to output the things I know I'm going to be interested in. And so then I could bring in, all right, this file goes on to this worksheet for beta 90 hot. This file goes on to this worksheet for beta 90 or beta 90 cold. This one goes on to this worksheet for beta 90 survival, and then as I run things over and over again, I just have to re-import those in, and then everything else is linking back to that. So I am very much a fan of bringing my data into Excel and manipulating it there, which is one of the reasons that I'm an advocate of numbering things in a way that I recognize what it is, rather than just auto-number everything and let the contour plots do what they want. If I know that node 1000 is the motor, then I can use that to my knowledge when I'm extracting data from the full set. Okay, so that was it for the building a thermal desktop model. How am I doing on time? 8 minutes late? Oh, I'm on time if I'm only 8 minutes late. So, all right, do we want to do a quick question and answer? Are there some questions before we move on to some of the other topics? Yes? So a contactor will take and subdivide the surface. So if I have this contacting here, it's going to take this and divide it into 10 surfaces, 10 small surfaces by 10 small surfaces. And here it's going to then look and see which of these tiny little small subsurfaces projects onto the node areas associated with the mesh underneath it. So yes, it's possible to get some places where 2 things line up and it might straddle a division between 2 sub areas, but it's generally close enough for our purposes to not be a problem. One more, might be something else I can show. One moment. Okay. So when you do contactor, so when I do a contactor marker check, and I see all these little yellow lines, So each of these yellow lines is a projection from the sub-element as it goes. So you can see here, this is making contact with the surfaces underneath it. If I was very worried about that, I could increase the contact intervals and say, let me make it 20 by 20 as opposed to 10 by 10 so that I get smaller areas associated with it to better align with the mesh underneath. Clear? Okay. You're welcome. Any other questions before we continue? So there's only so arbitrary that you can do with the basic orbit or the Keplerian orbit. But if you have close ties with your orbital dynamics team, you can get from them the vectors for the sun, the vectors for the Earth, and then the ratio or the distance from the Earth. And so you could say, okay, I've got this very complicated trajectory orbit, but most of their codes know where the sun is, where the Earth is, and you could then use a vector list for your solution rather than the orbital, which is assuming certain behavior of the orbit. So if you have a simple enough orbit, you might not be able to do it, but if you have a complex orbit, it might be easier or better to just get the direct vectors from your orbital dynamics team. Does that make sense? Okay. We use that very much for launch analyses where, you know, it's barbecue rolling and, you know, doing pivots and things like that. So, you know, it's much easier sometimes to just get the direct vectors. And if you look at a output file from the heat rates and look at the comments at the top, you'll see that for each orbital position, it has vectors for where's the sun, where's the Earth, and what's the ratio of the distance. So in the end, the thermal desktop code is just figuring out what those vectors are from the orbital parameters you gave it, and then solving, you know, there's the sun, there's the Earth, I'm this far from it, here's how I scale my fluxes. And here's where I'm in eclipse. And one thing to be careful of, if you say that the sun is there, and you say that the Earth is there, you're in eclipse. So I did have a time where, you know, we have a solar, an L2 orbit, and I said, okay, well, the sun's there, Earth's there. And I was wondering why I had no environments, because the sun's there. I didn't consider that it will say, well, the Earth's there too. So the Earth is between you and the sun, and so you're in eclipse and you get no loading. So. You can check, but it's more difficult to do. When you visualize the vector list, it doesn't show it to you about a planet anymore, but it will show you the vector, it'll draw it, where's the sun and where's the Earth. And it will tell you, I think it will color it purple if it's in eclipse. And so you might have to step through each one and understand where it is a little better. You're kind of going from a Lagrange to an Eulerian viewpoint. You know, I'm on the body and looking out, or I'm outside and looking at the body. But you can still verify it if you understand and know the orbital mechanics well enough. Not my area of expertise, but you could see where those vectors are pointing. having come from a time where we did more development of Cinda logic ourselves, it's comfortable to me. I'm also never quite sure how the cyclical nature works. You know, suppose the orbit period changes from one case to another, and I've put it in for one orbit case. Well, now I'm going to get slightly out of sync each time I go. Whereas if I control it, you know, it's a little bit easier for me to really know what's going on. I'm comfortable enough doing it in Cinda, so I'd rather do it in Cinda. You know, it also lets me say, okay, well, this is tied to eclipse, or this is tied to a certain amount of time. You know, yes, you probably could do it with a profile. I just prefer the alternate way. You know, the other advantage is that if I need to fail it, you know, it needs to be off for some case, I can do that. Not as easy to turn off a transient heat load unless you put a multiplier or something in there to do that. So I find it more flexible to use the Cinda approach than to use the time varying heat loads. So we'll mark this day down. In 1 year, I'll hope to have converted you. So yes, that is very specific. You could, if it were me, I would probably try to model the ribs and deal with the conductivity through it. By and large, if given the opportunity, I want my boxes to mount to the flat side of the panel, so I don't have to deal with that. But I know we have had pocketed panels like that before and tried to come up with, you know, a emissivity factor to account for the deepness of the pockets, and additional conductivity in X and Y for the rib behavior. But it is kind of make a more detailed model and figure out how that relates to my more simplified model and what correction factors I can apply to do that. But I would probably first try to model the ribs if that's not too much to do. And with elements, I think that it usually goes pretty easy. But if you have a whole lot of details in ribs and cutouts and different sizes and bosses, it could get more complicated than you'd like. So does that address your question or sufficiently dodge it? Okay. All right. So okay, go ahead. Okay. So that's the case where I would go bring some nice chocolates to my flight dynamics friends and ask them for the vectors of where the sun is and where the earth is as a function of time, and then reduce that down to a reasonable number of calculation points, because they could probably give that to you every minute, but you don't need it that frequently. But that's where I would rely on the flight dynamics. As soon as the orbit gets complicated, I find it easier to just fall back to vector lists where things are. We have a barbecue roll on Roman that is probably similar, where it's going like this. As it goes around the Earth, it's like, okay, I don't want to try to model that with basic orbit capabilities. Let's get the vectors and then solve it from there.
Okay, thank you.
One other thing to be cautious of, if you happen to have a barbecue roll that is at a certain rate, you want to avoid solving at a rate that's an integer multiple of that. So let's say I spin one revolution every 60 seconds. Well, I don't want to solve every 30 seconds, because then I'm getting this side, this side, this side, this side, this side, this side. I'm missing all of the points in between. So find a random prime number somewhere in there that gets multiple points as you're rotating around. And then thermally, when you're solving, also do that, because you don't want to solve your calculation points at an integer multiple of it, or you're going to always get the same loading on the same sides and not get the behavior. So think about that when you have something that's rotating, to introduce some quasi-randomness in so that you're not always solving at the same point. And that came from years ago. We were at S-Tech testing a satellite, and the data collection system was every 2 minutes, and the satellite was rotating 1 revolution per minute. So we always got the exact same flux there, and we're wondering why the steady state numbers didn't match up. So think about the cadence that you're solving and the cadence that you're rotating to make sure that you're not always solving the same orientation. So,
thank you.
Okay. All right, so let's move on in the interest of time. You can tell me to hurry up. Time to break. Okay, good. Maybe we'll do a slightly shorter break. So are we talking about the cutoff for each ray, so the minimum energy, and not the cutoff for how many rad Ks, or the minimum rad K to include? Is that correct? That will be coming up very shortly in the radiation calculations. So if you could see if that question gets answered in about 20 minutes. And if not, we'll ask again, because I think that's covered.
Okay.
Yes. So generally, I think you want to go from the smaller surface to the larger surface. If I'm trying to contact this water bottle to this table, I want to divide this into as many small points and deal with the mesh here. If I went the other direction, this table to this water bottle, well, now I have all these other points along here that aren't anywhere near the water bottle. It would only be 1 or 2 that make contact here. So generally speaking, it's best to go from the smaller surface that you're subdividing to a small and fine enough granularity that you catch large portions of the sub-mesh underneath it. Make sense? Did it answer the question? Okay. Not sure I understood the question. let me try to answer it and tell me if I did it. Domain tag sets are almost like an alias or a symbol for surfaces. So I've defined that there may be a domain tag set called box baseplate. And so I can put surfaces into box baseplate later, but I could make contact to box baseplate now. And it will figure out when it makes the contact or when it does the calculations, it will see what surfaces are defined in the domain tag set then. So it's almost a container for you entering something later, a node, a set of surfaces, and so on and so forth. It can be used just as groups. It can be used for establishing contact between objects. It can be used for applying a heat load to something. The place I've seen them specified most in terms of a requirement is usually at an interface, a spacecraft, spacecraft to a launch vehicle will have a particular interface. They'll want you to put your surfaces that interface to them into a defined tag set so that they have already made the contact to that defined tag set. They just need to know what surfaces go into that. So you could use it as a placeholder at interfaces between organizations if you wanted to specify it as a requirement. Does that answer the question, or did I miss it?